unpaired electrons which will be responsible for the magnetic properties in the coordination compound. Ligands which play a very important role when it is bonded with the central metal atom. If the ligands are different, the colors is also get different. So what is the metal carbonyl indicates that? The metal which is get bonded with the carbonyls, and carbonyls are nothing but a ligands. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with a unit called coordination compounds. Under that, we have discussed about the magnetic properties of the coordination compounds, and also we have learned about the limitations of valence bond theory, and also we have learned about what is crystal field splitting. Under that, we have deeply discussed with crystal field splitting of octahedral as well as with the tetrahedral complexes, and we also discussed about the spectrochemical series which tell us about the nature of the ligands which will be acting with the metal ion. Is it right? And also we have learnt about the electrons in the d orbitals of the metal ions. How does it forms octahedral complexes and tetrahedral complexes also we have learnt. Today let us move on to the last topic of this unit by understanding the color in the coordination compounds and the influence of the ligand on the color, and we are going to understand the limitations of CFT and the bonding in metal carbonyl, and we are also going to understand the stability of coordination compound and applications of coordination compounds also we are going to discuss in this session. Let's see what is a color in the coordination compound. So we already understood that from the magnetic behavior, the presence of the unpaired electrons which will be responsible for the magnetic properties in the coordination compound. Is it right? Yes. Like that, the color in the coordination compound will also be explained. How does they'll take the solutions of the coordination compound when light which is passed over on it, it will absorb the radiations in the visible region and get reflected back with the different colors. That is said to be the colors in the coordination compound. So, when the white light is passed to the solution of transition metal complexes, the solution absorbs certain electromagnetic radiations of wavelength. The color of the complex is complementary to that of which is observed. For example, let us consider this is a color wheel. You can imagine that suppose if you pass the white light to the transition metal where it absorbs the wavelength region around 590 to 630 and it absorbs the orange color, and when you are looking at that entire solution which give rise to the blue color, blue color. This is known as complementary color, or you can say that it is complementary to which it is get observed. Okay, that is known as what? The color in the coordination compound. Similarly, suppose if the light is passed to the coordination compound solution where it absorbs the yellow light, corresponding to this, you can see that violet light will be observed to the observer. Similarly, if the color is allowed to pass through the coordination compound, it will be in the form of red light. The observer will see that the formation of the green color. This indicates that color which is get absorbed, which is complementary to the color of the color which is get observed. This is how the coordination compounds which gives a complementary color when a white light is passed to the solutions of coordination compound. So hope you are understood with this topic. We'll see with few examples so that you will understand how does the color will be obtained due to the different ligand. So we have the coordination complex like this, that is COCl NH3 5 times, and the name of the coordination compounds will be goes like this: pentamino chlorido cobaltate 2. Is it right? Yes. And it will be absorbed in the wavelength region around 535, and it is absorb the yellow light, and the complementary entity is violet color. Okay. Similarly, we have removed the chlorine. Instead of that, we have added the water here, and the name of the compound will be goes like this: pentamino aqua cobaltate 3. So it will be absorbed in the wavelength region around 500. So when it is absorbed the green light, it gives rise to what? Red color. Okay. Similarly, we have one more compound where it consists of 6 amine group. So it is hexamino cobaltate 3, and it absorbed in the visible region of wavelength around 475, and it absorbs the blue light and it gives a yellow orange color. Next, we have 6 cyanido or hexacyanido cobaltate 3 ions. It is absorbed in the wavelength region around 310, and it will be fall in ultraviolet region so that it is not visible to the naked eyes, but when it is absorbed by the observer, it gives us to what? Pale yellow color. Similarly, we have one more complex. It is tetra aqua copper 2 plus ion, which is absorbed in 600 wavelength, and when it is absorbed the red light, it gives us what? Blue color. Similarly, we have a last compound that has hexa aqua titanium 3 plus, which is absorbed in the wavelength around 498. When it is absorbed the blue-green color, which gives us what? Violet color. This shows that even though the compounds which consist of different ligands, their color will be different. Is it right? Yes. So this indicates that ligands which play a very important role when it is bonded with the central metal atom. If the ligands are different, the colors is also get different. So this shows that our coordination compounds, when it is made it in a solution form, when you pass the white light, it gives us to the different colors because it absorbs the different colors in the visible spectrum region. Now let us see the color in the coordination compound by taking one example. Okay. So I'll take the example of hexa aqua titanium 3 plus ion. We know that it will be present with the violet color. Is it right? Yes. So it is an octahedral complex with a single electron titanium 3 plus, where it consists of one electron in the 3D system, and the metal d orbital which will be consists of that electron will be present where? In the T2G level. You can see that this is the energy level diagram for the titanium. Okay, in that you can see that it consists of how many electrons? It consists of what? One electron in the 3D system. So that one electron will be present where? In the T2G. Okay, it present in the T2G. You can see that one electron I have shown here. Okay, so next to the higher state which is available for the electron. So you can see that this is the energy level diagram for hexa aqua titanium 3 plus. Is it right? Yes. So in the ground state, we have understood that it consists of one electron in the 3D system, and in that it will be present in T2G level. Is it right? I have written a one electron. When it is absorb the light, what will happen? It get excited. As a result of this, the electron which is present in the T2G level has got shift to the EG level. And give rise to the different colors. This is how, we can easily understand that how the color will be formed in a coordination compound. This is known as complementary to one another. Okay. So, what will happen? Again, I can explain here. You can see that. So, this is a ground state of the titanium, hexa-aqua titanium, which consists of one electron in the 3D system. So, that one electron will be present where? In the T2G level. When it is absorbed the light, what will happen? This one electron has been shifted to the EG level in the excited state and gives a different colors. So, if the light of corresponding energy of yellow-green region is absorbed by the complex, it would excite it to the electron from T2G level to the EG level, and the electronic configuration I have written here, and thus the complex will be appear to be violet in color. So, why it looks violet color? Because it absorbs the light in which region? Yellow-green visible region. Okay. So, yellow-green is a visible region for the titanium, and when it is get absorbed, it gives rise to what? Violet color. It gives rise to what? Violet color. And the crystal field theory attributes to the color of the coordination compound due to the DD transition. So, why it is also known as DD transition? Because the electron which is there in the 3D system has got shifted to the EG level, and again this is an 3D system only. Is it right? Yes. So, the electrons which is get shifted between the DD orbital, hence it is known as what? DD transition. So, this was explained based upon the CFT. Okay. This is how, by taking the hexa-aqua titanium 3+, we can easily understand that how that coordination compounds which gives a different colors when it is absorbed that different color. Okay. So, hope you have understood this, and I can write the electronic configuration here. In the ground state, it consists of how many electrons? T2G, which consists of 1 electron, whereas EG has 0 electron. There will be a no electron. Whereas in the excited state, the T2G, which consists of 0 electron, whereas the EG level, which consists of what? 1 electron. Why it is transferring its electron to the excited state? When it is absorbed the white light. When it is absorbed the white light in the yellow-green region, it gives to the violet color. So, hope you all understood this. You can understand the same thing here. So, you can see that this is a yellow-green visible region, so which has been absorbed by the titanium and give rise to what? Violet color. So, this is a violet color of the titanium complex, or you can say that it is a hexa-aqua titanium 3+. Next, we will understand the influence of the ligand on the color. So, by understanding the color nature of the coordination compound, we also observe that even though when you replace the ligands, the color of that coordination compounds will become different. So, now let us take an example so that you will understand how this ligand which play an important role when giving a color to the coordination compound. The absence of the ligand, the crystal field splitting does not occur, and hence the substances will become colorless. If there is no ligand, what will happen? There will be no approaches to the central metal atom, so that central metal atom will not get shifted to the higher energy state, and there will be no splitting of EG and T2G will be taking place if there is no ligand. Is it right? So that substances will become what? Colorless. Only when the ligand is there, there will be a lot of approaches will be taking place between the metal as well as with the ligand. So that splitting up of metal ions with the different two sets of energy will be also taking place and give us to the particular color. So let us take an example here. In the hexa aqua titanium 3 chloride, you can see that if you remove the water from this complexes by heating, so it will become what? Colorless. It will become what? Colorless. Similarly, the anhydrous copper sulfate is white. When you dissolve it in a water, it will become a blue in color. This indicates that ligands play a very important role to give a color to the complexes. Is it right? Yes. So you can take this example. Here my ligand is my water. Is it right? Which has been coordinated with the titanium, which is a central metal atom. And this chloride is a counter ion. Is it right? Yes. When you remove this water, which is nothing but a ligand, the entire complexes will become colorless. Is it right? Similarly, you can take one more example, the copper sulfate, which is a white crystals. Is it right? When it is dissolved in water, it will become a blue color because the water will be itself act as a ligand and it will get coordinated with the copper and forms a copper complexes. This is how the ligands, which play a very important role in giving a color to the coordination compound. Let us take one more example. I'll take hexa aqua nickelate 2 plus complexes. So which forms nickel 2 plus nickel 2 chloride when it is dissolved in water. So what will happen? This entire complex which forms what? Nickel 2 plus chloride when it is dissolved in water. So I'll consider hexa aqua nickelate 2 plus. So when it is dissolved in water, so what does it give? It gives a nickel chloride. It gives what? Nickel chloride. So if the bidentate ligand such as ethane 1,2 diamine, which is progressively added to this complex, what will happen? In the ratio of 1:1 or by 2:1 or by 3:1, the series of the chemical reactions will be taking place. So what will happen here? Please see, here I am taking the hexa aqua nickelate 2 plus complex. If you dissolve it in a water, it forms what? Nickel 2 plus chloride. Nickel 2 chloride complex will be formed. To this, if you add the bidentate ligand such as En, which is nothing but a ethane 1,2 diamine, series of the reactions will be taking place. So here I have a series of the reaction. So where you can see that, so nickel hexa aqua nickelate 2 plus, if you add the ethane 1,2 diamine as a ligand in a 1:1 ratio, it forms what? It removes the 2 water molecule and get added up with the En and forms the plain blue color. Again, if you add the one more 1,2 diethane in a 2:1 ratio, again it removes 2 more water molecule and it becomes what? Diaqua diethane 1,2 diamine nickelate 2 plus ion. Is it right? And it gives what? Purple blue color. Similarly, if you replace 2 more oxygen by adding the ethane 1,2 diamine as a ligand, all the water molecule will be get removed out and it will become what? Violet in color, and it is named as triethane 1,2 diamine nickelate 2 plus ion. This indicates that even though the ligands are different, the color which is formed, which is also get different. This indicates that ligands are very important for the coordination compounds to form a color. Is it right? You can see that how does it forms a pale blue as well as with a bluish purple as well as with a purple color when it is reacting with the different ratios of the what? Ethane 1,2 diamine ligand. This is how we can easily understand that the ligands which play a very important role in giving color to the coordination compounds. Next we have the limitations of CFT, that is crystal field theory. So already we have understood that by knowing the crystal field theory, it is very easy to predict the geometry, it is very easy to predict the crystal field splitting of the coordination compound. Is it right? But somehow it do not explain the certain criteria which is there for the coordination compound. Let us see now. The crystal field model is successful in explaining the formation, structure and color as well as the magnetic properties of what? Coordination compounds. But it do not explain the certain things. They are nothing but the crystal field theory assumes that ligands are nothing but a point charge. Is it right? So it considers that when the ligand is approaching to the metal, the ligands are considered to be point charges, and it follows that anionic ligand should exert the greatest splitting effect, but anionic ligands are found to be at lower end of the spectrochemical series. This is one of the biggest disadvantages as we have seen in case of the CFT. Is it right? So when we are understanding the CFT postulate, we have understood that the metal, when the ligands are reacting with the metal, the type of the bond is said to be ionic. Is it right? And we say that these ligands are of two types. It will be sometime anionic and it will be also neutral. Is it right? And this anionic ligands, we have understood that it will be experiences a greater repulsion, or we can say that this anionic ligands can experience the greater splitting than that of the neutral ligand. Is it right? But actually while studying the spectrochemical series, we have understood that all these anionic ligands which comes under the last part, which are the least ligands which are undergo the crystal field splitting. This is another disadvantages, and it does not take an account to the covalent characters of bonding between the metal with the central metal atom. According to the CFT, it says that the bond between the metal and ligand is ionic. It does not account for the covalent nature, and it does not tell us about the color of the substances when it is considered fully as well as with the empty d orbital. It is very important. It does not account for the coordination compounds even though it consists of full or at the empty d orbital. How does the splitting will be taking place was not explained by CFT, and these three are the limitations to the CFT which was not explained by the CFT postulates. Okay. Next we have bonding in metal carbonyls. So what is the metal carbonyl indicates that the metal which is get bonded with the carbonyls, and carbonyls are nothing but ligands. Is it right? Yes. It is together known as what? Metal carbonyls. So the homolytic carbonyls are the compounds which consist of carbonyl ligands only, are formed by most of the transition elements. Here we have a certain example. You can see that this is tetracarbonyl nickelate and it is exhibit in a tetrahedral structure. This is my central metal atom which is surrounded by 4 carbonyl ligands. Similarly, we have one more example where you can see that this is pentacarbonyl iron 2, and you can see that it will be exhibit in a trigonal bipyramidal structure. You can see that this is a central metal atom surrounded by 5 carbonyl group. Is it right? Yes. Similarly, we have one more complex is carbonyl chromium, where it consists of central metal atom as a chromium surrounded by 6 carbonyl group and forming a metal carbonyl compounds. Similarly, we have one more example. This is decacarbonyl manganese, which consists of 2 metal ion or 2 metal atom surrounded by 5 carbonyl group. Surrounded by what? 5 carbonyl group. And we have one more example, that is CO8CO2. In that you can see that between the CO and CO you can see that like a bridge it will be formed. This indicates that metal carbonyls are very stronger, as we have studied with the coordination compound, and it is one of the special case where the metals are directly bonded to the carbonyl group. So now let us see how does the bonding will be there in the metal carbonyl. So in the metal carbonyl, always it involves in the 2 types of bonding. One is sigma bonding and another one is pi bonding. So I'll take out the example of the metal as well as with the carbonyl group. We know that the metals which consists of pair of electron. Is it right? Yes. So this pair of electrons which is found in the metal, it always donated to the vacant d orbitals of the carbonyl group, and hence it forms what? Pi bond. Similarly, the carbonyl group which consists of the electron which will be donated to the, this is a vacant site. Vacant site or the vacant orbital. The vacant orbitals of the metal to form a sigma bond. This is how both sigma as well as the pi bonds will be formed between the metals and the carbonyl. Hence, it is known as synergic bonding, which means to say that if pi bonding is there, the sigma bond will get stronger. If sigma bond is there, pi bond will get stronger. This is said to be the synergic bonding. And also, we use a common term known as back bonding. What does it mean? Already I have explained that the electron which is present in the central metal atom in the last shell, it is always donated to the carbonyl group which consists of what? Vacant site. So what will happen? This electron are always donated to the anti-bonding orbital. Anti-bonding orbitals of what? Carbonyl group. Hence, it is also known as what? Back bonding. This is how the metal, when it is reacting with the ligands, it involves the 2 types of bond. One is sigma bond, other one is pi bond. And we need to understand the stability of this coordination compounds also. So this will be explained by using stability constant. The stability of a complex in a solution refers to the degree of dissociation between the 2 species. Which are the 2 species here? 2 species are nothing but a metal and ligands, and it is involved in the state of equilibrium. Let us consider a reaction where the metal is allowed to react with the ligand to form a metal ligand complex. Okay. So this will be explained by what? Stability constant formation. And let us write the stability constant, that is nothing but a beta, which is equal to, this is a molar concentration of the reactant divided by molar concentration of what? Product. So how I have written the stability constant? Stability constant will be obtained by what? This is a molar concentration of the product divided by molar concentration of the, this is a reactant and this is a product. Okay. So this is how we can easily explain the stability of the coordination compound that is written in the equation form. Okay. That will be expressed by using what? Stability constant beta, where it is obtained by the ratio of molar concentration of the product divided by molar concentration of the reactant. For this reaction, greater the value of stability constant, greater is the proportion of Ml4 in the solution. Suppose, imagine your stability constant is increases means there will be a greater formation of this product in the solution. Is it right? So, there will be a greater formation of product in the solution when stability constant is high. The free metal ions are really exist in the solution, so that metal will be usually surrounded by the solvent molecule, which will be compete with the ligand molecule and successfully replaces with the formation. You can see here, when metal reacting with the ligand, it forms what? Metal ligand, and the rate equation will be written like this: Ml divided by M into L. What does Ml stand here? Ml stands for the product and M into L are nothing but a reactant. Similarly, the Ml complexes again, if it is reacting with the ligand, it forms a Ml2 complexes, and the rate equations will be written as Ml2 divided by Ml into L. Again, this is my product and these two are the reactant. Again, this complex, if it is reacting with the ligand, it forms a Ml3, and you can see that Ml3 is a product divided by Ml2 into L2, which is a reactant. Again, this Ml3, if it is reacting with the one more ligand, it forms a Ml4. Ml4 is my product and Ml3 into L is my reactant. So here I have written K1, K2 and K3 and K4. They are referred as stepwise stability constant. They are referred as what? Stability constant. So that we can easily write it as M plus 4L, which gives us to the Ml4, and the stability constant, which is also written as beta 4, which is equal to Ml4 divided by M into L to the power of 4. Why it is L to the power of 4? Because the 4 ligands are reacting with the metal to form a Ml4 complexes. So that the stepwise as well as with the overall stability constant will be relate like this. So B4, which is equal to K1 into K2 into K3 into K4, or in general we can write that beta n is equal to K1, K2 or K2, so on up to the Kn. So here the reciprocal of formation of the constant is known as instability constant or dissociation constant. This is how we can easily understand the formation of the coordination compound in terms of stability. So, we will discuss lastly with the applications of coordination compound. So, we have many applications. We will discuss one by one. In many qualitative and quantitative chemical analysis, the color of the reactions will be given by the metal ion with the number of ligands, which helps in detection as well as with the estimation. So, if the complex which consists of the different ligand, we already understood that ligands are responsible for giving color to the coordination compound, so that during the analysis or during the estimation, it is very easy to identify the color of that given complexes. Even though the hardness of the water can also be estimated by simple titration of Na to AdTA, which forms a stable complexes known as Ca2 plus and Mg2 plus ion. So, this is another important applications of what? Coordination compound. And the articles which is also get electroplated with the silver, gold, much more with the smoothly even with the solutions of the complexes to give dicyanide organocomplexes or silver complexes that forms a solution of simple metal ion, and some important extraction process of the metals such as gold and silver, which makes use of the complex formation. So, in your first PUC, hope you have studied with the general principle and process of isolation of the elements. In that, we more talk about the complexes. Is it right? That complex which is formed by reacting in the metal with the ligands. So, that will be also useful in the process of isolation as well as within the extraction. Next, the coordination compounds are also used as what? Catalyst. For example, in the Williamson, reaction, we use a Williamson catalyst, and it is known as PH3P whole bracket 3 times rhodium chloride, which is used in hydrogenations of what? alkenes. And chelating therapy, it is used in medicinal chemistry. For example, EDTA will be used in treatment of lead poisoning, and some of the coordination compounds such as cisplatin and related compound to inhibit the growth of the tumors. So we are very much familiar with the cisplatin, which is one of the treatment which is given to the cancer patient to remove the tumors which is formed in the different organs of our body. During the treatment of the cancer also, we use the coordination compounds, and coordination compounds have a great importance in the biological system. For example, the chlorophyll in the coordination compounds of the magnesium, hemoglobin, in coordination compounds of the iron and the vitamin B12 are the coordination compounds of the cobalt. So these are the important applications of the coordination compound. Remember, from this application we can expect one mark question. So have a look out with the applications and try to work hard. By this I like to say that I have completed the important things in the last session. Try to note down. We'll meet you with the next chapter. Till that, take care, be safe. Thank you.